Okay, good morning. So we'll get started. So far we have discussed about some basic concepts in real-time operating systems, and then we have examined the available operating systems, both open source and commercial. So today we will examine that for a given application, how do we select a computer for real-time application, or if the hardware is fixed, how do we select an operating system out of several available operating systems to meet the requirements of our application. So let's proceed with that. So we had just started this last time, that if you are asked to select a computer system for a given application in mind, the computer will be used for a specific purpose. How do you go about selecting the computer? Because there are several vendors, several types of systems with different configurations and so on. So I had posed this question yesterday, and we had given the example of a web service, that what do you do to select a computer to host a web server for an organization. And then some of you had said that MIPS and FLOPS rating, etc., can be used to distinguish between different systems. But then we had said that there is a big problem with the MIPS and FLOPS rating. These are misleading. Why are these misleading?
Correctly representing the current CPU usage.
Not clear. Correctly represent CPU usage means what? Anyone else?
Number of instructions may vary. Each instruction size may vary. So each
So,
instruction may take different time.
Okay. So what you are saying is that the different instructions can take different times to execute. But then what's the problem?
The number of instructions, billions instructions per second, is not standard measurement. So
No, what do you mean by standard? Yeah. So the MIPS rating are usually quoted by vendors with respect to the shortest instructions, because after all, they will take some programs and execute, or maybe they will just take the average of all instructions, depends on how to compute, because MIPS, how to evaluate MIPS, there is no standard definition. So somebody can even take the shortest instructions and see how many instructions can be executed per second. But actually, when you bring the computer and try to run your application will have a different mix of instructions. Maybe it does lot of I/O each time a web page is loaded, needs to do I/O and also networking, right? So lot of I/O is involved and very less ALU operations. But if the rating is computed, the shortest instructions are ALU operations. So in that case, it will be highly misleading. Do you agree with that? Okay. So later the PIC, MIPS and FLOPS were quoted by vendors implicitly with the understanding that they are expressing the performance of the computer with respect to the shortest instructions, or the instructions that execute in the shortest time. But still that does not help. I mean, it says that it has some peak performance with respect to the shortest instructions. But as far as your program is concerned, you are not going to use those instructions, right? So even if you compare the PIC MIPS or PIC FLOPS, it hardly helps as far as your selection for a web server application is concerned. Is that okay? Okay. Let's proceed. So this exactly just saying this, that the peak processing speed computed by the shortest instructions and other instructions are ignored, I/O and those instructions, and it becomes misleading. Later, I mean, once this was known that MIPS is a problem, everybody agreed that MIPS is a problem. So, the first thing that one would think of is that why not run one program, some program, and then say whether it performs well with respect to that program. And that was the concept of a toy benchmark. In a toy benchmark, some of the standard programs are run. For example, quicksort, merge sort, operating on some large amount of data. They can quote that how much time it takes to quote 100,000 integers using quicksort on that computer, right. So, that gives some indication of the performance, but again the basic problem still remains. It just tells how well or how fast it computes merge sort or quicksort. It does not tell how well it will run as a web server, because the web service will require a different mix of instructions as compared to a quicksort or a merge sort. So, the solution is possibly to use a synthetic benchmark. See, the best thing would be to actually get the computer, I mean all the computers that you are trying to select, and then run web service and then measure the performance. But that is practically impossible. You can't do that. You can't get all the vendors to get all their computers here or operating system and then you evaluate performance. It's impractical, because they won't give you the computer to experiment. It will be too expensive, and also to install and run, it will be not a practical solution. So, the solution that was considered was a synthetic benchmark. So, we were just discussing this yesterday, that in a synthetic benchmark, the instruction distribution over a large number of programs is analyzed. So, what is the frequency of different instructions that occur in a variety of programs, and then you take the average and then find out in a typical program, that is average program, how many ALU instructions, how many IO instructions, etc. Different categories of instructions you can find out for a typical program, that is average program, right. And then you can synthesize a program or write a program which has that many percentage of ALU, let us say it has 12% ALU operation. So, what you can do is give first 10% or let us say 100 ALU instructions, right, that is 12%, I mean as the distribution is, then write the IO statements. And remember that this program does nothing, it is not doing anything meaningful, but the only thing is that it has the required distribution of the instruction set as an average program. So, it will give you an idea of how an average program will run on this computer. So, helps to some extent, but not really, isn't it? Because web server is not a average program, it is a specific program whose instruction distribution will be different from an average program, but still it will give a good indication. Now, let us see what are the other solutions. So, let us look at the synthetic benchmark. The synthetic benchmark is written with which fulfills the average instruction distribution, and there were many synthetic benchmarks which were popular. The Whetstone, Drystone, Linpack, etc. These were popular those days, about 20-25 years back, but this had a problem that we were discussing yesterday. The problem was that the manufacturers, they optimized their system with respect to this benchmark, because they know finally they will have to quote with respect to a Whetstone or a Drystone benchmark, and these are the source code of this is available, Whetstone, Drystone, etc. And you can easily analyze what kind of instructions they use, what exactly they do, and so on, and you can write a compiler which will either generate instructions that take the shortest time, or it can make some optimizations, simplifications of expression evaluation and that kind of thing. So, that runs well for that program optimized to run that program well. So, that is a problem, is not it? Because again it depends on how well the compiler is optimized. Based on that, the performance will be reported. So, then what can be done? The spec benchmarks have become very popular over the last 15 or 18 years. SPEC stands for Standard Performance Evaluation Corporation. It is a non-profit organization. You will get information from www.spec.org. You can download the benchmark programs, the source code also. And there are various types of benchmark programs. We will just look at them very briefly. For example, okay, I think SPEC 89 was the first one, and then SPEC 92, 95, 2000, etc. So, the SPEC 89 had a problem, the same problem that Drystone etc. had. It included a small kernel called as matrix 300, a small part of the code which is executed as the inner loop, right. It is executed maximum number of time, which consists of a 300 by 300 matrix operation. So, that is carried out many times, and by optimizing the inner loop, somebody can improve the performance by a factor of 9. Just see, by writing the compiler carefully and just targeting that inner loop, somebody can improve the performance by a factor of 9. And also for the Drystone, somebody can discard 25% of. If you look at the Drystone benchmark code, you can see that many of the code can be just the compiler can discard it without executing. For example, I was giving an example of if one do something, right, that always evaluates to true. So, that means that instruction will anyway be executed. So, why do we need a if instruction? And then the benchmark suits were used. Here it is not just one program based on which the benchmarking is carried out, it is a suite of different programs. So, you can't just optimize one part of the code. And because you want to choose computers for different applications, there are, if you look at the SPEC website, you will see various benchmark programs. For example, SPEC View for Perf for graphics performance, 3D graphics, visualization, content creation and so on. JVM 98 for client side virtual machine, JVB 2000 server side Java application, Web 2005 web servers. So, possibly this is the one you should use, this benchmarking. You would ask your computer vendors to quote the performance with respect to Web 2005 benchmark, and then it will give you a fairly good idea about how the computer system is going to perform when used as a web server. If you look at the program here, the source code, if you download from SPEC site and examine, you will see that there are multiple workloads utilizing the HTTP, HTTPS and also dynamic content, PHP, JSP, etc. Again, this will not be a precise measure of the performance, because your organization might finally be using a static web pages, and then this will be slightly off the benchmark, I mean the actual performance that a computer will show, but still it will be fairly close. Now, let us see how do you benchmark real time computers. You want to select computers for some embedded or real time application. What do you do? You have to first of all consider, identify some parameters that are important for a real time applications. What are the parameters for that are important for a real time application? Can anybody say some few parameters? No, scheduling algorithm is your choice.
system of
Timer.
has to be in microseconds than in seconds. Order of
So you mean the finer the timer, the better it is?
yeah.
Not really. See, your application might need a 10 millisecond timer or a 100 millisecond timer. What do you do with a nanosecond timer?
Not all the case, but it has to be finer in terms of real time systems than the normal systems.
Okay, not really. Let's see what are the parameters that we can consider. The task switching time, task preemption time, interrupt latency time, semaphore shuffling time, deadlock breaking time, and datagram throughput time. So these are some of the important parameters. We will see that, and later, see, this we are talking of a real stone metric. We will look at different metrics, and then we will see that there are other parameters also not included in the real stone metric, which are important.
Is
Yes.
there any significance of that edge? It is all wet stone, dry stone, real stone.
Okay, see, I mean, he is asking an interesting question. He says that, see, wet stone, dry stone, etc., and this is real stone. So, is there a reason? See, the only reason that one can think of is that you go to a goldsmith and ask him that how, what is the quality of this gold. He will take out a stone, he will rub it, right, and he will tell you what is the quality of the gold. And maybe, I think so, that these, I do not know, I mean, it is not written anywhere, but possibly that is the reason that this is like a stone with a goldsmith. You take the stone and try to benchmark different computers, possibly that is the reason.
Also, there is a hedge extra in all these words.
I do not know, I do not know why it is extra. Sorry, any other question?
Sir, there you had said there will be 7 components, but we have listed 6.
Okay, so maybe I just missed here. We will just see the details of this. Okay, yeah, right. So he says there are 7, but there are 6. He has counted it here. So I think one I have missed here. I think the process preemption time. No, the task preemption time is there. We'll see. I think there is one more there. It's, as we proceed, I'll just tell you. But this is not really the exhaustive set of metrics that we can use to measure real time performance. We will see that there are many more important parameters that are not really mentioned. We'll discuss about them in different metrics. I mean, this one has proposed this set. Okay. So here it is there. I did not show it. The process dispatch time. So let's see what these mean. The task switching time is the time the system takes to switch between 2 independent tasks. So let us say T1, T2, T3, sorry, T1, T2. Now let us say for some reason T1 blocks need to start T2. So how much time does the system take here to do this switching from T1 to T2, context switching basically? First we will see the times, I mean the parameters. Later we will consider how to really evaluate them. I mean, can you write a application or a program which will evaluate them? Because if you can do this, write your own, or we will see that the programs that we are saying, these are just examples. The way you will compute this, these are examples, not that that is the only way you can do that. Maybe you can think of a better way of measuring benchmarking real time computers, and you can publish that, because not much result, if you look at the literature, not much results are available on benchmarking real time programs, but still it is a very practically important problem. So let us see what are the parameters and what are the ways we are suggesting. I mean, the literature suggests that this should be evaluated, and then you can see that there are many other ways you can do it. So it can be a good exercise if you try that. Okay, let us proceed. So the task preemption time. So here, if a high priority task has become enabled or has just arisen, it should get the CPU, isn't it? Because it is a preemptive priority based system that we are discussing. So, the task that is involved here, the work that is involved is recognize the event causing a high priority task to become ready. So, the event occurs with a sensor or something, and then it takes time for the event to be registered by the processor, and then the operating system has to access the priorities of the tasks, see that this is a higher priority task, and then it takes time for context switching. So, context switching time or the task switching time will be less than the task preemption time, isn't it? Because there are other activities involved here. The interrupt latency time. This is the time when the CPU receives an interrupt. So, from the time it receives an interrupt to the time it executes the first instruction of the ISR is the interrupt latency time. So, let us say it was T1 was executing, and at some point the interrupt occurred, and it takes certain time before the interrupt service routine starts executing, the first instruction starts executing. So, the time it takes between the event causing the interrupt event to the first instruction of ISR getting executed is the latency time, and of course, this is the important criterion as far as real time processing is concerned, because if a task needs to complete after the occurrence of an event within certain time, then if too much time is wasted here in the as interrupt latency time, then we have very little that we can do to run the task and meet its deadline. So, this has to be low, the interrupt latency time has to be low. Okay, that is the interrupt latency time. Unbounded priority inversion prevention time. Whenever a high priority task requests a semaphore, a shared resource, then what is the worst case time delay that can occur? So, the worst case time delay will occur when a low priority task is holding the resource and intermediate priority tasks are not allowing the low priority task to complete. Unbounded priority inversion will occur and it will take long time. So, this parameter represents the effectiveness of the supported mutual exclusion scheme, or what is the scheme used to avoid unbounded priority inversion? Is it just an inheritance mechanism? Is it a ceiling protocol, locker protocol, etc.? Or is just ordinary operating system does not do anything specific as far as request by a higher priority task is concerned. So, okay, there is some problem with the diagram. Okay, we will just look at those two parameters little later. The dispatch time, this is the time the real time process waits for some external event to be activated. So, the time interval between the system receiving an interrupt request and beginning of the application task. So, just see, this is different from the latency time, isn't it? It includes latency time in fact. See, after an event occurs which is supposed to start a task, for example, let us say temperature became high and a task handling that event needs to execute, then first the interrupt latency time will be incurred, and then the ISR will start executing, and then the context switch will occur, and then the task will start running. If we look into details of the latency time, we will see that it is the hardware delay. The hardware delay basically the sensor recognizing the event and the event reaching the computer takes time for it to be reported, and the time to finish the current instruction, and then latency time. So, the hardware delay is the time required for the hardware or the sensor to notify the processor. The latency time is the interrupt handling function prepares the system for execution of the interrupt routine, basically save the context and all those. So, if we see here the different component of the process dispatch latency time, you will see that there are three components. One is the interrupt latency time, and then interrupt routine execution, and then the context switch. So, the interrupt latency time is the initial hardware delay for the sensor to recognize the event and then to be reported, time it takes till it is registered with the CPU, the time it takes to finish the current instruction T2, T3 is the latency time, and T4 is certain pre-processing that is done in the interrupt routine, the ISR, and then the ISR executing, then some post processing that needs to be done, and T7 is that once the ISR completes, the OS to recognize the need for context switch, and then the final context switch time. So, let us just see some two parameters that we left out. Okay. So, let us see in a reduced size. So, here see the task T1 is a low priority task. On the y axis we have the priority of the task, and on the x axis we have the timeline, right. So, the T1 task was executing, and at certain time T1 acquired a resource, and then a high priority task T2 started executing, and then another task T3 started executing, and so on. And the high priority task T3 requests the resource that T1 was holding, the same resource. So, naturally there will be a context switch, but T1 won't immediately start executing, because T2 was preempted by T3, and in between there may be several other tasks that might come in. So, if there is not a proper prevention mechanism or priority inversion, it will take long time, and finally T1 will get its turn to execute and then complete, and then it takes certain time for T3, basically the context switch time, for T3 to start executing. So, the priority inversion prevention time is basically the sum of TA plus TB, right, and if there is not a proper mechanism in place, TA will take long time. Another parameter we did not see is the datagram throughput time. As we are saying that many applications need to transfer data between one process to another. So, this is the time that takes for sending certain kilobytes of data from one task to another by using the system call, rather than writing data to some shared memory and then another task reading it. Okay. So, let us proceed with our discussion. So, the parameters that we are looking at are actually the integrated set of the performance of the computer. I mean, most of them are based on the computer, the hardware, and also the operating system, isn't it? There is also another one which is called as the tridimensional measure. It says that, see, there are three things we need to consider. One is the MIPS speed, and we know that MIPS speed has problem. The second is millions of interrupts per second, which is MIPS 2, MIPS 1, MIPS 2, and then the IO throughput in millions of basic IO operations per second, and then the volume is computed as M1, M2 into M3, and this measure, the tridimensional measure, is volume to the power 1 by 3. So, basically it takes not only the MIPS rating into picture. I mean, if you have only MIPS rating available, then you can at least consider the interrupt handling per second, number of interrupts handled per second, and the IO throughput. Another factor that is considered is the interrupt processing overhead, and this can be easily computed through an experiment. So, it basically defines how long it takes to complete an application at a specific interrupt loading. So, let us say interrupts occur, for example, network transfer is occurring at certain place, or let us say disk IO is occurring, or page fault by other applications is occurring. So, that time one task takes how much time to execute, or a sensor is keeping on giving interrupts. So, how much time does a certain task take to execute? So, the interrupt processing overhead, is Tn minus T0 divided by T0, where Tn is the time the application takes when there are n interrupts per second, and T0 is the time it takes when there are no interrupts, divided by T0 into 100. For example, if the application takes, when there are no interrupts, takes 1 second, and when there are 20,000 interrupts occurring per second, see, here we are talking of the application which is not needing these interrupts. These interrupts are occurring and the system is just recognizing them, and they are not processed. And for this task, the high priority task, which is not affected by the interrupts, takes 1.6 second, then what will be the interrupt processing overhead? It will be 1.6 minus 1 divided by 1 into 100, which is basically 60%. So, for this specific computer, which runs the task in 1 second when there are no interrupts, and it runs the task, same task at 1.6 second when there are 20,000 interrupts occurring per second, then the interrupt processing overhead will be 1.6 minus 1 into 100 is 60%. And if we find that there is another computer for which the interrupt processing overhead is 80% for similar situation, obviously this one would be better for a real time application. Now, let us see some operating system benchmarks. We will consider two main benchmarks. One is called as a deterministic benchmark and the other is a latency benchmark. We will just see what are those. The deterministic benchmarks, they measure the determinism of the operating system services. So, basically, whether there is a jitter in the timer. So, when a timer is set to expire, Does it give precisely the time at which it is to be given, or is there a variation in the timer time that is reported? If you set a 1 millisecond timer, does it report at 1.01 millisecond, or does it report at 0.99 millisecond, or does it give at exactly 1 millisecond? We will look at another parameter, the response and also the bin time. So, let us see these parameters. Okay. So, here we have described what exactly this involved in a timer jitter parameter and how you can measure. In the timer jitter, we create a periodic timer, set a periodic timer basically, and then measure the deviation between the desired and actual expiration. So, set it for 1 millisecond, 10 millisecond and 100 millisecond, and then check, keep on checking what is the maximum time by which it differs from the expected time. So, look for some 100 or 200 or maybe 1000 readings of this timer, and then check what is the maximum discrepancy that occurred. But then you would ask me that how do you find the discrepancy, because the timer you set for 1 millisecond or 10 millisecond, how do you find the discrepancy? So, that we will just see shortly how do you find the discrepancy. So, here it measures the response time of the operating system. Basically, the timer will report the event, right. It is not that the timer did not work, the timer has reported the event, but it is the operating system which has taken time to respond, or it has taken different amount of time each time the timer has given a interrupt. We will also consider the response parameter as a deterministic benchmark. Execute a fixed processing load and then see how much time does it take each time. Does it take the same time, or is there a variation of the time that it takes? The typical processing load that we might consider may be Whetstone, maybe some benchmark, spec benchmark. It may be simple add programs or copy simple ALU programs. The idea is that when you run a thread, will it complete in a deterministic fashion, and remember that we are considering a real time priority, the highest priority. It should not happen that the kernel is doing something internally, handling the timer response or something, and then depending on how many reports or maybe interrupts occurring for other tasks, it's just taking time to handle those, and in the meantime your task is getting delayed sometime, is completing early sometime. And then we will look at another parameter, the bin time. Here we will call the time of the day clock to report what is the current time, and then measure the interval between calls. So, basically how much time it takes to complete the bin time. Here we are just notice here that we are just keep on invoking a system call. See the difference between this and this, the response and the bin time is in the response we are trying to execute a thread, that is a user thread, but here we are trying to execute a system call and then trying to see how much time it takes to report that the time, and here we are measuring the maximum kernel blocking time. So, this is about testing the timer jitter. See, we have set a periodic timer. So, the timer period is between the time it was set from time 0 to 100, 200, 300, 400 etc. But see at different times the timer is being reported at different places, right. See here it is almost nearly 200, here it is 320 or so, and so on. So, the timer jitter is the maximum variation. So, here the maximum variation that has occurred, here the variation is less for each of them, here the variation is maximum, and that we are calling as the timer jitter. Let us see how to set up an experiment to measure the timer jitter. First is to create a timer through system call, and while creating the timer, we set it to expire at some time, maybe 1 millisecond, 10 millisecond or 100 millisecond, basically at few different values that are comparable to the task that we were or application that we are considering, or to set it. And then when it expires, determine the actual expiration time. But how do you determine the actual expiration time? So, you set it to expire at 1 millisecond. How do you measure the actual expiration time? Yes, anybody would like to comment anything? See the problem here. The problem that we are asking is that, see, you were set up an experiment, you written a small C program. So, it can be a good small project also. You are trying to benchmark different real-time operating systems. So, what you have done is, the first parameter trying to check is that what is the accuracy of the timer interrupts, right? You set a timer, periodic timer, and what is the accuracy at which it is reporting the events, right? And here you have just created a timer and then trying to measure whether it has exactly given at the same time. But the question is that how do you measure? So, you set at 10 millisecond, let us say. So, it has given you a timer interrupt at some time, right. So, then how do you know that whether it has given you exactly a 10 millisecond or is it 10.1 millisecond or 11 millisecond? How do you know? So, that is the question we are asking. Yes, anybody would like to answer anything? A small experiment, you can do it, very simple experiment. All of these benchmarking programs will see simple experiments.
Set that timer some n number of times, and then so that
no, how do you compute the jitter? See, what he is saying is that set it to expire for a million number of times and see what is the time at the last instant, and then see. No, that does not help, because see, it is each time the timer gives an interrupt, how much time it takes to handle the interrupt, I mean report the interrupt. The interrupt is occurring. See, if you do that, the last one will also be not very far off from the reading, and then you divide it by million, you will get 0. Okay, not very hard. Basically, you will have to read the time value, isn't it? So, most of the operating systems, they either have a hardware clock where you can read the time value directly, or you can read the time value, the precise time value, or the clock reading. You can read the clock, but through a system call or directly. Let us see that. So, the jitter is the deviation between the actual and the desired expiration times. Okay, it should be the maximum. The jitter is the maximum deviation. So, to compute jitter, you will have to consider all deviations and then select the maximum among them. So, if you take just 2-3 readings, then you may not notice the maximum. You have to take thousands of readings, thousands of deviation values, and select the maximum there. So, all real time operating systems, they would include a timestamp counter, and even in the POSIX ACTI, POSIX real time, we have the clock get time system call. See, either you can directly read the counter, or you can give a call, the clock get time call, and this will give the high precision time of the day, which will be a large number. You can even try on your Linux machine. You use the clock get time, it will report you a large number, basically the number of clock readings that have expired since the clock was boot, maybe the clock reading, right. But what you are interested here is the difference between two times. It is not the clock time, it may be a large number, not bothered about that. You have to take the difference. First take the clock reading and then keep on taking the readings each time the interrupt occurs. Take the difference and that will tell you how much time has expired since the interrupt has been reported, right. Now, let us see how to measure the response. So, here we have a fixed block of processing, let us say some 10 millisecond or something, which may be a, you have written a small program with some ALU operations, add, etc. Or it may be some benchmark program, spec, or maybe a Drystone or something. So, here you are trying to determine whether the time that it takes to execute is deterministic or not. And remember that the task that you are running here is a real time priority task, and a real time priority task should not take different times, at different instances of run. Otherwise, no, your scheduling routine, you can't really assume that it takes that much amount of time. You have to take the maximum in that case. Sometimes it takes less time, sometimes it takes more time. Then your scheduling algorithms, in the analysis, scheduling analysis, you will have to take the maximum time. So, here you will run it several times, and each time use the time of the day clock get time, and measure how much time it takes. So, you can try with different types of tasks, some may be some additions, subtractions, etc. Another may be involving memory copy, data transfer, and so on. Another may be synthetic benchmark. Let us look at the bin time. So, the bin time you can use to find out how much is the kernel blocking time. It said that almost every system, sometime or other, the interrupts are disabled, and as long as it is in the kernel mode, it takes different amount of times depending on what it is doing in the kernel. Or for systems that do not even consider this, how much time it is in the kernel mode, maximum time. So, it may be in the worst case, if you once you make a system call or another task is making a system call, how much time does it take to complete. So, repeatedly call the time of the day clock and calculate the time required in each clock, and it would indicate the time the interrupts are blocked. So, each time you are just trying to execute something, a fixed routine, and that too as a at the real time priority level, and then you are finding that at different times it is taking the same one taking different times, and obviously the kernel is getting blocked by some other system calls. Of course, one thing that is remained unsaid here is that you keep on calling the kernel with from another task, keep on giving system calls. Otherwise, if there are no system calls by another task, this may not show variation. So, let us say there is a very low priority task which is keeping on giving system calls, or maybe it is doing IO, disk IO or something, or networking, and then this high priority task which is running and trying to give system calls, what is the variation in the time? So, here of course, if we decompose these times, it will be the time to perform the system call and the time to do mode change if required. So, the deviation between the maximum and minimum time will give an indication of the time spent in the kernel. So far, we looked at the deterministic benchmarks, which basically tell us that whether timer runs deterministically, it reports the timer deterministically reports the events, whether a thread runs deterministically, and whether each time you make a system call there will be a variation in the time. Now, let us look at the latency benchmark. The latency benchmarks are sync, which measures the latency of thread to thread or process to process synchronization. So, how much time or how much overhead is there in synchronization, because resource sharing will be required, and if the operating system has too much overhead in doing synchronization, then you will have to factor in that time in your scheduling, and where we just assume that it is almost nothing, the synchronization time, isn't it? I think when we were doing the examples earlier, we had considered something on context switch and so on. Synchronization time, we had almost ignored this while doing the analysis of resource sharing. But if it is a significant time, the operating system implements a very inefficient synchronization mechanism, then of course, our scheduling analysis will be wrong. So, here it considers the context switch and handling the resource. See, basically when it requests for a resource, it undergoes a context switch and will measure that time. So, the type of semaphores that we will consider, that can be considered is the POSIX recommended named and unnamed semaphores. Then the message passing, which measures the latency of sending data from one thread to another thread. So, this is a simple parameter to measure. We will see how to measure all of these. So, this measures the possible throughput of data between processes and threads, and we will use different data buffer size, and then we will measure the latency of real time signals between two processes. So, once a real time signal occurs, how much time does it take for the signal to be reported, because the different tasks will communicate different events through signals. So, the latency of the POSIX real time signals will be measured. I think we were discussing about the POSIX real time signals in the context of POSIX real time. We had said that the requirement, the difference between a standard signal and the POSIX real time signal, does anybody remember what is the difference? We said that the POSIX real time standard, the signals has something extra compared to standard signals. Okay, so that is your homework, just recollect that how is the POSIX real time signal different from standard POSIX signal. So, we will use the experiment, we will use an experiment to measure the real time signal latency. So, we will stop now and we will continue from this point onwards in the next lecture. Okay, thank you.